Hello, in this video I'm going to go through a couple of pretty basic momentum questions just so we can get an idea of what we're doing with conservation of momentum to make sure we haven't got any misunderstandings, and then we can use that as the foundation when we move into dynamics and look at things in a little bit more detail. Right, so in this first question we've got a child of mass 48 kilograms standing at rest on a stationary skateboard. The child jumps off the skateboard, initially moves horizontally with a speed of 1.2 meters per second. Skateboard moves with a speed of 16 meters per second in the opposite direction to the direction of motion of the child. So find the mass of the skateboard. Okay, so we need to do a sort of before and after type thing going on here. It's nice to have a standard approach. So we can do before and we can do after. We probably want to mention somewhere as well that we're doing conservation of momentum, so we can make a note of that. And then we can say initially our momentum is 0 because everything's stationary. The child's not moving, the skateboard's not moving, so we've got nothing at the start, and that is going to be equal to what we've got going on afterwards. We're assuming this is a closed system. It hasn't given us any reason to think otherwise. And the child is moving at 1.2 meters per second and he's 48 kilograms. So we've got 48 times 1.2. That's our amount of stuff, 48 kilograms. We're using our operational definition of mass here by just saying this is whatever the scales are telling us it is. We're not getting into any kind of theory on the structure of matter or anything. We've got 48 kilograms of stuff moving at 1.2 meters per second. So momentum is those things multiplied together. The skateboard's moving in the opposite direction. It's going at 16 meters per second. So we're going to have to put a minus in there because this is all vector stuff going on here. Momentum is a vector quantity, so we need to have that as minus 16 meters per second if we've got plus 1.2 meters per second for the child. And then that's going to be multiplied by some mass m of the skateboard. So we can say that 48 multiplied by, I'll call that 6 over 5, is equal to 16m. So we can divide by the 16 and say that m is 18 over 5, which is equal to 3.6 kilograms. So yeah, pretty straightforward really on all of this. You can see we're going to get ratios here of if these things need to be conserved, the ratio of the speeds is going to be the same as the ratio of the weights. So the 1.2 over 16 is going to be the same as the 3.6 over 48. It's going to be in that same proportion in order to make these things add up to 0 again. And you're going to get a lot of that proportion type stuff coming through in these conservation of momentum questions. Right, looking at the second one, we've got two particles moving towards each other. So we can say, again, let's set out a thing. We've got conservation of momentum, just so we can convince people that we know, what we're doing and what we're applying here. We've got before and we've got an after. And then we've got A and B. So A is moving at 6 meters per second for a mass of 3 kilograms. So we've got 3 times 6. B is 2 kilograms and it's going in the opposite direction at 8 meters per second. So minus 2 times 8. And that is going to be equal to whatever happens afterwards, which is the particles collide, coalesce and moves with speed v. So the total mass then is 5 kilograms multiplied by v. So we've got 2 is equal to 5v. So v is going to be equal to 0.4. So yeah, pretty straightforward stuff. We then have the particle collides with a stationary particle of mass m, and they coalesce again. Okay, so we've got another one. So we've got another, so let's call it, I don't know, second collision, or at least after the second collision. And then we can say here that, well, this has got to be, again, equal to the total mass times the new velocity. Or, I mean, we could also think of this, so that's the 0.1 times the 5 plus m. Could also think of this again in terms of the proportion of stuff again. I mean, the amount of momentum provided by this 5 kilograms after the second collision has dropped down to a quarter of what it was originally, because our velocity has gone from 0.4 to 0.1. So if we're getting a quarter of our original momentum from these particles, the new one must be the other 3/4. So m is going to have to be 15 kilograms in order to make up that difference. Or that's the same as solving this equation. You know, 2 is equal to 1/10 of that, so 20 is 5 plus m, m is 15. So it's all that proportion stuff coming out again. It doesn't really matter whether you just want to stick with solving the algebra or thinking about it in a you know, a more sort of conceptual way. It's nice to think about it in two ways. You know, it's always, the more ways you can think about things is often the better. It sort of expands your understanding of things, doesn't it? And you get to see patterns. But yeah, like I say, a fairly simple start, but we'll use this as our foundation going into dynamics.